Okay, so let's take a look at section 3.4. Okay, 3.4 really covers two different things, rational zeros, okay, and synthetic division. Okay, synthetic division is a shortcut to doing some of the types of division problems we did yesterday, so it will save us a little bit of time. So when you have a function, you can kind of break down the roots into two different categories, rational roots and irrational roots. For now, we're going to ignore imaginary roots. We won't be pretty soon. But for now, we're just going to classify roots as either rational or irrational. Well, there's a theorem that helps us to list all the possible rational roots. Okay? We can come up with a list. And that's called the rational root theorem. The rational root theorem is pretty easy, okay, but I'm going to show you the language that I use to kind of set up the description of it. Uses some math symbols, so I'm going to explain what they mean if you don't know. Okay, this is a polynomial, starting with your highest degree term, and then the coefficient of it, and then the next highest degree term and its coefficient, all the way down to the linear term, and lastly the constant. Okay, so that just represents a polynomial. In the next part, I will read to you step by step. Okay. This symbol means for all n, so that means for every value of n. So whether n is a sub 1 would be the first coefficient, so on. Bless you. Okay, so for every value of n, a sub n, which a sub n is the number in front of x, it has to be an element of the rational numbers. Okay, so what I'm saying is here, every single coefficient has to be rational. So you're not going to have a polynomial with something like this. Technically that's a polynomial, but some of the coefficients are irrational. Okay. I'm saying that all the coefficients have to be elements of the rational numbers. They all have to be rational. And there's one particular restriction on the first coefficient and the last coefficient, a sub n and a sub 0. They can't be 0. So this theorem will not work if the first coefficient or the constant are 0. Okay, so let's look at what the rational root theorem says. Again, assuming that's our background. We have a polynomial with rational coefficients. Okay, if something is rational, it can be written as a fraction. Okay, I'm using the letters p over q. So let's suppose that x is a rational root. Okay, it's an x-intercept. When you plug it in, you get 0. Okay, if it's rational, I can write it as p over q, where p and q are two very special things. P has to be a factor of the constant term, okay, the last term, a sub 0. And q has to be a factor of the leading coefficient. Those are the two things that are really important here. Okay? The leading coefficient and the constant. I don't really care too much about everything else if all I want to find are the rational zeros. So p has to be a factor of the constant, and q a factor of the leading coefficient. So let's look at an example. I want to list all possible rational zeros to that polynomial. Now, notice what I'm saying up here. I'm not guaranteeing you that every single one of the numbers in this list is going to be a 0. I'm just saying we're going to have a list of possible zeros. That's all the rational root theorem does, is it gives you a list of possible roots. Which ones are roots? Well, we could use the calculator and a couple other techniques to help us check that. So let's list all the possible rational zeros. First thing I've got to do is figure out what's P and what's Q. Okay, so P. P has to be a factor of the constant. Okay, Brianna, what's my constant here? -6 is my constant. So I want to list every single number that divides evenly into -6. Okay, Darren, can you give me my factors of -6 or +6? They have the same factors. Yep. 1, 2, 3, 6. Okay, and make sure that we include positives and negatives. Okay, so positive or negative 1, 2, 3, and 6. And Q. Q is all the factors of the leading coefficient. Okay, so I need all the factors of 10. James, what are my factors of 10?
1, 2, 5, 10.
1, 2, 5, 10, and what else? That's half of them.
Oh, negative.
The negatives, yeah. So positive or negative 1, positive negative 2, 5, and 10. Now we just have to write every single possibility you could have. Now you don't have to write the positive and the negative. Just use the plus minus symbol. Okay. But let's write them all. So try to use a systematic way of doing it. I generally let Q be, say, 1. And let's go through all the p-values. Okay. So we could have, so this is our list of possible rational roots. We could have 1 positive or negative 1 over positive or negative 1. Okay, and I'll reduce it as we go. We could have positive or negative 2 over 1. Positive or negative 3 over 1. And positive or negative 6 over 1. Okay, now let's go to the next value of Q and go through all the values of P we could have. So we could have positive or negative 1 over 2. Positive or negative, let's see, 2 over 2. But do we already have that one? Yeah, so let's not repeat it. Positive or negative 2 over 5. And positive or negative 2 over 10, which reduces to 1 over what? 1 over 5. Okay, so we're just listing every combination, P in the top and Q in the bottom. Okay, now let's go to the next value of Q. Positive or negative 1 over 5. I already have that. Okay, so we're not going to repeat it. Positive or negative, well, somebody tell me what would the next one be? So I'm using this value with all the different P's. So I checked 1 over 5, I already have it. The next one is, yep.
3 over 2.
Oh, did we miss? Oh yeah, thank you. So 3 over 2. Yep, and yep, 3 over 5. Just a couple. And was there anything else? 3 over 10. Okay, so we listed 3. Did we miss anything else there?
6 over 5.
Yep, let's look at 6. We have 6 over 1 we already have, 6 over 2 we already have, 6 over 5 we don't have. And 6 over 10, do we already have that one? Yeah, 6 over 10 would be the same as 3 over 5. So let's see how many we've got. We've got 4, 5, 6, 7, 8, 9, 10, 11, and let's see, there's one more. We've got 6, we've got 1/2, we've got 1/5, 1/10, I think we're missing. Yep, positive or negative 1 over 10. Okay, so here's a list of all the possible rational roots. There's 24. Okay, which ones are actually roots? Well, we have to use the graphing calculator to go through, check them and see. Okay, but try to be as systematic as you can. Okay, come up with a system for listing all the possibilities. Okay, any questions on that? And that's it. Some of them don't have this many possibilities. It's just P had quite a few factors and so did Q. So we had a lot of different options to list. Okay, now we're going to use the same problem we just had. And I want to prove that this equation only has one real root and that it's irrational. Okay, let's graph it. Okay, so actually it's right over here. So 10, scroll down. So 10x to the fifth minus 3x squared plus x minus 6. Okay, so 10x to the fifth minus 3x squared plus x minus 6. Okay, there's my graph. So I can pretty clearly see that there is only one real root. Okay, it crosses the x-axis here one time. And let's find what that root is. So second calc 0. Okay, pick a point to the left, to the right, and do your guess. And it says the root is point. Let me check. Did I type that in right? Oh, no, that's supposed to be a plus. Okay, so make sure you have that as a plus. Or minus, sorry. All right, let's check the root again. Second calc root. Pick a point to the left. Right, and guess. And this time we get 0.9505. That's correct. How can I prove that 0.9505 must be irrational? And you got to think about what we did in example 1 and combine it with what we just did in example 2. Yeah?
You make sure it's not, if you convert it to a fraction, make sure it's not one of the possible.
Yeah. This is the list of all the possible rational roots. If 0.9505 isn't one of those fractions, then it's not rational, because those are the only rational ones. And none of those fractions are 0.9505. 1/2 is 0.5, 1/5 is 0.2, 3/10 is 0.3, 3/2, that's bigger than 1. So none of these fractions, if you change them, are 0.9505. Okay? So the root is 0.9505 roughly, that's approximation, and it is not listed as a rational root. And this is not in the list of possible rational roots. So the only conclusion, if it's not in the list of possible rational roots, it has to be irrational. Okay? So it must be irrational. So this time, using the rational root theorem, gave us a list of possible rational roots. Unfortunately, none of them are actually roots in this problem. None of them. All 24 of them. They don't work. Okay, any question on that? Okay, so that's the rational root theorem. We'll try another one with not so many options in a little bit. So the next thing is a shortcut for using long division in certain cases. It only works if you're dividing by something that's linear. If you're creative, maybe you can figure out how to make it work for cases where it's not a linear denominator. I'm not going to show you that, but might be able to extend what I'm teaching you a little bit. But we're just going to stick with cases that are linear. Okay, so step one. You're going to write down the number that appears after the minus sign. And you're going to put this bracket around it just to kind of separate it. And then we're going to write down all the coefficients of f of x. Just the coefficients. When you do synthetic division, it's all numbers. You're not writing any letters through this whole process. As you write your coefficients, make sure you fill in zeros if there are any powers that are missing. Just like we did with long division. Yeah?
You have to write down what's the, you have a C with bracket on that.
Yeah, and then all these dotted lines would be your coefficients. Okay, when we go through an example, synthetic division is extremely easy. It's just explaining it is kind of weird without an example.
So write down, right?
So you're going to write down C, put that bracket, and then you're going to put all your coefficients. You might have something like this. You know, if you were dividing, say, 4x squared plus 5x plus 2 by x minus 3, this is how you'd set it up synthetically. Put the number after the minus sign on the outside, copy down the coefficients of the polynomial you're dividing into. 4, 5, 2. Okay, next you're going to bring down the first coefficient. Okay, I'll go through a real example in a second. Okay, you're going to bring down your first coefficient. Next, you're going to take that number you just brought down, which is the first coefficient, and you're going to multiply it by the number that's on the outside. You're going to take that answer, and then you're going to put it in the second column. So you're going to bring down a number, you're going to multiply it by what's on the outside, you're going to put the answer in a second column. Then you're going to add together the numbers that are in the second column. And that's basically the process. You keep multiplying, putting the answer in the next column, and then adding, getting a result. Take the result, multiply, put it in the next column, add the two, get the result. Okay, you just keep repeating that process until you're done. Okay, now once we're done, then we have to interpret our answer. So the very last row, okay, when you do this process, contains two things. One, it contains the coefficients of the quotient. Okay, it contains all the coefficients of the quotient. Bless you. And the second thing it contains is the remainder. The very last number, the number all the way on the right, that is going to be your remainder. Okay? So the number all the way on the right is your remainder. All the other numbers are your quotient, coefficients of the quotient. Okay, so we'll go through a few examples. Make sure you see how to do this. Okay, let's start with this one. I want to show that 3/2 is a 0. I want to show that it's a root. What's another way of saying that? If 3/2 is a root, then what must be a factor? Right, x minus 3/2 is a factor. And that's really what I'm going to do. I'm going to take 2x cubed minus 5x squared plus x plus 3, and I'm going to divide it synthetically by this. So what I'm really going to show is that x minus 3/2 goes into my numerator without a remainder. But if something divides in without a remainder, that means it's a factor. And yesterday we had a theorem. If it's a factor, it's equivalent to also being a root. So that's how we're going to prove it's a root. We're going to show that this factor divides in evenly. So start by taking the number that would be after the minus sign. Put it on the outside, put a bracket just to separate it. And now write your coefficients of your numerator. 2, -5, 1, and 3. If I was missing a term, I would have filled in a 0, but I'm not missing any. Okay, so I just did step 1. Step 2, bring down the first coefficient. Okay, so we're going to bring that down. And I put a line there just to kind of separate my results from kind of the calculations I'm doing. All right. Next, step 3. Multiply the divisor, 3/2, by the number I just wrote there, 2. What's 2 times 3 divided by 2? 3. Write the result below the second coefficient. Now add the number you just wrote and the second coefficient. What's -5 plus 3? -2. Okay, now we do it again. What's -2 times 3 divided by 2? Oh, Cole? What's -2 times 3/2? Your denominator here is the same as what you're multiplying by, so it cancels out, right?
Yeah.
So what would you get?
3. -3.
-3. Okay. So now we have 1 plus -3 is -2. We'll try it one more time. -2 times 3/2 is
1.
same question we just had before. What's -2 times 3/2?
3.
So if you have 3/2 and you multiply by -2, the 2's cancel, and all you're left with is 3 times negative, which is -3. Right, now we add these up. What's -3 plus 3? 0. That's my remainder. So what we just showed is that that divided in evenly. There's no remainder. Right? And now let's look at what our quotient is. Okay? That part is the quotient. Okay, so your remainder is 0, and your quotient are these numbers. Okay, so you got to figure out what this means. So this is your constant, the -2 all the way on the right. The next one is your linear term. The next one is your quadratic term. And then the next one would be your cubic term as high as you need to go. So this is the constant. This is the linear term. And that's the quadratic coefficient. So your quotient is 2x squared minus 2x minus 2. Okay, any question on that? Right, so now they ask us to write it in factored form. So the original problem was 2x cubed minus 5x squared plus x plus 3. Well, we already know that x minus 3/2 is a factor. We proved that. Times our quotient. 2x squared minus 2x minus 2. So each time you divide something in, the quotient that you get is going to be 1 degree smaller than what you started with. Okay, what can we factor out of that quotient? Yeah? A 2. Watch what happens if you factor out a 2. Just put the 2 on the outside. You get x squared minus x minus 1. But I'm going to take the 2 and I'm going to redistribute it back to the other factor. And what's that going to do to this fraction? If I take and multiply, if I distribute the 2 out, 3 divided by 2 is going to turn into what? Oh, Alex?
3.
Yeah, it's going to get rid of the fraction. That's why I'm doing it. So I have 2x minus 3 times x squared minus x minus 1. That's as simple as you can write it. X squared minus x minus 1, we can't factor that easily anymore. Okay, any question on that? So that's how you can go about factoring something that's more complicated. You got to start with at least one root that you know, or you can check on the calculator. And then you divide it into it. Okay, it's kind of like if I said to factor 100, and you didn't know how to do it. And I said, well, 2 is a factor. You could say, all right, well, he told me 2 is a factor, so I'll start with that. Take 100, divide it by 2, get the quotient. The quotient is 50. That's what we just did in this step. Now you could work with 50, and you could say, all right, now I can factor that some more. Right? But you got to start out with something that you know is a root, and then it'll make the quotient smaller than what you started with. Okay, any question on that? That was synthetic division. Let's try another one. Okay, this time I want to find the quotient and remainder. So I'm not guaranteeing you that anything is a root here, so you might not get a remainder of 0. So when we set it up synthetically, what number is going to go on the outside of that bracket? Yeah? -3, very good. So it's the number that's after the minus sign. In this case, think of it as x minus -3. Okay. What about my numbers that I'm going to write up at the top for my coefficients? Victoria, what will those numbers be?
3.
Okay, yep, 3's good, 7's good.
1.
Close. You gotta be careful though. We forgot something. What did we forget? Yeah?
When there's a missing 1 and put the 0.
Right. So we forgot the 0 for the x squared term. So we should have a 3, 7, then a 0, then a 1, then a -11. Okay, let me do this problem more at like a regular speed and show you, how quick it can be to do synthetic division. Bring down your 3. 3 times -3 is -9. Take 7 plus -9 is -2. -2 times -3 is 6. 0 and 6 is 6. 6 times -3 is -18. -18 plus 1 is -17. -17 times -3 is a positive 51. And then 51 plus -11 is 40. That's the whole problem, using synthetic division. So now let's actually find the remainder and the quotient. Hey, Darren, what's my remainder?
40.
Yep, remainder is 40. And now these are the coefficients of your quotient. So let's figure out what the highest degree term has to be in our quotient. So Kelsey, what's the highest degree term going to be?
4.
Well, this is your constant. Always start with that. So this is the thing without the variable. Yeah, it's going to be a degree 3. So we need a 3x cubed minus 2x squared plus 6x minus 17. So there's your quotient and remainder. So is x plus 3 a factor of that original polynomial? You think, Andy? Okay, who can help? What are you looking for to determine if something is a factor? Cody? Only one number there you really need to focus on. Yeah? The remainder. Okay, you're just looking at the remainder. And what would you want the remainder to be if it was a factor?
0.
0. In this case, the remainder is not 0. So that means x plus 3 is not a factor of that. It does not divide into it. Right, we did that with long division yesterday, seeing if something was a factor. Today we got a little faster way of doing it. All right, so this time, this is kind of getting at what I was just saying. I want to show that something is not a 0. Okay, in other words, I'm going to show that this whole thing is not divisible by x minus 3. So I'm hoping that I don't get a remainder of 0. Okay, Colby, what's going to be the number on the outside for our synthetic division?
30.
Yep, it's the number that's after the minus sign, or the root, or the 0 in this case. 3. And my coefficients, it looks like I have everything I need. 2, 5, -2, -3. Okay, Colby, what's my first step?
Bring down the 2.
Perfect. Bring down the 2. And we multiply. 3 times 2 is 6. Augustine, what do I do with the 5 and 6?
Combine them, which makes 11 times 3, 3.
Yep. Go ahead, keep going.
Then that goes times 31.
Mm-hmm.
Times 3 is 93.
Mm-hmm.
Minus 3 is 90.
And what's that 90? That's my
Remaining.
remainder. Since I got a remainder of 90, x minus 3 does not go into that evenly, which proves 3 is not a root, or it's not a 0. Had I gotten 0 for the remainder, then that would mean 3 is a root. Right? But in this case, it's not. Any questions on that? So some of the strategies that we're going to use for finding roots, along with what you already know from Algebra 1 and 2, like factoring and quadratic formula, we're going to use the rational root theorem, along with a graphing calculator and synthetic division. Our goal is to somehow, we're going to list all the possible rational roots, use the graphing calculator to narrow that list of possibilities down, and then if we find one that looks good, we're going to divide through by it synthetically. Because if we divide through by it, it's going to take the cubic, it's going to make it a step smaller, a degree smaller. It'll make it a quadratic. And then we have many ways we can finish off a quadratic. Hopefully factoring if it factors. If not, quadratic formula. The graphing calculator. So let's start with the rational root theorem. We'll make a list of all possible rational roots. So Emily, P we said earlier has to be a factor of what?
The last number, the coefficient.
All right, so P has to be a factor of the last number, which is this time it's just a 2, or -2. Alex, what are my factors of 2?
-1, -2.
And
Plus or minus.
plus or minus, yeah, there's not many options here. Well, there's even fewer options for Q. Okay, this time my leading coefficient is a 1. So the only factors of 1 are 1 and -1. Okay, so Casey, what would my possible rational roots be? There's only 2 of them.
1 and 2.
Oh, actually, I'm sorry, there's 4 technically. So positive or -1 and positive or -2. Now what I'm going to do to narrow that down is I'm going to graph it and see if any of those possibilities look like they could happen. Okay, so let's graph x cubed minus 3x minus 2. X cubed minus 3x minus 2. Looks like -1 could be a root, and it also looks like 2. Okay, let's check -1. So we're going to divide through synthetically by that, and hopefully get a remainder of 0. Okay, so let's check -1. If it's not -1, it's pretty close to it, so hopefully this works. So we're going to have 1x cubed, 0 for my x squared, minus 3 minus 2. Okay, let's go through the synthetic division. Bring down your 1. 1 times negative 1 is negative 1. 0 plus negative 1 is negative 1. Negative 1 times negative 1 gives me positive 1. Negative 3 plus 1 is negative 2. Negative 2 times negative 1 is 2. And negative 2 plus 2 is 0. So we've just shown negative 1 is a root, which Augustine means what is a factor?
One is root. I mean,
We've shown that negative 1 is a root.
so x plus 1
Yep,
is
is a factor. So we factored it into x plus 1 times my quotient, which is x squared minus x minus 2. And that's equal to our original problem, x cubed minus 3x minus 2. Okay, so we have at least one rational zero. Let's factor the second part and see if we get some more zeros out of that. If we hadn't found that first root, we wouldn't be able to do the kind of factoring we're about to do right now. So that's why we had to find at least one to start. Okay, so we've got x and x. What do my signs have to be when I do that factoring? How about Colby? Yep, I'm going to have plus minus. Two numbers that multiply to give me 2, 1 and 2. In this case, you want the 2 to have the negative and the 1 to be positive. Let's check it. X squared minus 2x plus x is minus x. 1 times negative 2 is negative 2. Okay, so let's list all our roots. We already know negative 1. We got that one. We got negative 1 again when we factored the quadratic. Does anybody remember what that's called if it occurs more than once? That's a repeated root. Okay, it's a repeated root, which means the curve is going to come up, it's going to touch the axis right at that number, and then it's going to go back away from it. And you can see that's exactly what happens at negative 1. Anytime a curve comes up, it just touches and goes away. That's usually a repeated root. And there's one other root we get. How about Darren? 2. So those are the roots, negative 1 and 2. And that's the process pretty much every time. Use your rational root theorem, then use a calculator, then use synthetic division. And the synthetic division will take your cubic, and it'll bring it down to a quadratic, which is easier to work with. We have 2 more, they're both the same. Let's do this one. Okay, how about coding? What did we say earlier? P has to be a factor of what?
Of the constant.
Yeah, P is a factor of the constant. So this time we don't have many options at all. The constant is a negative 1. The only 2 factors of that, positive and negative 1. Okay, and Q, Brielle, has to be a factor of what? Yeah, factor of the leading coefficient, which is 6. Cole, what are my factors of 6?
6, 2, 3,
Yep, and what else? That's half of them?
plus
Plus
and minus.
or minus. So 1, 2, 3, 6, and all the negatives. So my rational roots. Emily, what are my possibilities for rational roots?
Plus or minus 1,
Mm-hmm.
positive or negative 1 over 2,
Yep.
positive or negative 1 over 3, and positive and negative 1 over 6.
Okay, so now we have an idea of what the possible rational roots could be. Let's narrow that list down a little bit. And if we can find one that looks good, we're going to divide through by it. And it'll again take our cubic down to a quadratic. All right, so we got 6x cubed minus 5x squared plus 3x minus 1. Okay, so what looks like a pretty reasonable guess here for a root? Yeah, 1/2. Looks like it's between 0 and 1. I'm not sure if it's 1/3. It could be, but it looks pretty close to a half. So let's divide through by 1/2 and see what we get. 6, -5, 3, -1. It's the quotient that we're interested in, because the quotient is going to allow us to find the other two roots. So bring down to 6. Half of 6 is 3. -5 and 3 is -2. Half of -2 is -1. You get 2. Half of 2 is 1. Okay, we kind of expected that. It looked like it was a root. It goes in evenly. So we've got x equals 1/2. And now we have this 6x squared minus 2x plus 2. Okay, what can I factor out of this? Yep, James? A 2. So we get 3x squared minus x plus 1. And what I want to do now is, this doesn't factor. It won't factor. So how else can we solve a quadratic besides trying to factor it? Darren? So we have to do something special to solve a quadratic. We're not going to be able to get x alone without using a formula. What's the formula you use on a quadratic? The quadratic formula. Okay, so now we have to use the quadratic formula to solve for x. Right. I'm not even going to go through the whole formula. I just want to check the thing under the root, the discriminant. Okay, watch what happens. You get b squared, so it's -1 squared, minus 4 times a times c. What kind of number is that? 1 minus 12? So that's b squared minus 4 times a times c. A is 3, b is -1, c is +1. What do you get when you do 1 minus 12? -11. Now that's under a square root. It's the square root of b squared minus 4ac. That's the discriminant. What happens when your discriminant comes out negative? Yeah? Yeah, you'd be getting into imaginary numbers, which we're not going to find the imaginaries. They just wanted to know rational zeros. Rationals are within the reals. Right? You can ignore this whole part, because the answers to that quadratic are imaginary or complex. Right? And to check that, all I did was find the discriminant. Okay, remember, we checked that at the beginning of the year. We had 3 cases. If the discriminant comes out positive, there's 2 answers. If it comes out 0, there's 1. If it comes out negative, there's no real answers. Right, so that's a quick check on that. Yep.
So the rational 0 would be from him,
That's it.
and there's no real solution.
Yep, that's the only real solution, 1/2. And we could see just by looking at the graph, it never comes back and touches that axis again. Otherwise, there would have been more real solutions. So there's only one.
What's the whole discriminant thing?
The discriminant? The discriminant is this part of the quadratic formula. It's b squared minus 4ac. That tells you how many real roots you're going to have. If it's greater than 0, you get 2. Equal to 0, you get 1. Less than 0, none. And that's all because this is under a square root, and you can't take the square root of a negative.
But didn't we just get a negative?
What's that?
Didn't we just get a negative?
We got a -11, so now the next step would be to take the square root of that. If you were doing the quadratic formula, and you can't take the square root of -11, because it's imaginary.
Yeah. You just said, but we do have a root.
Yes, we got this root way back at the beginning from our rational root theorem. So we used our rational root theorem, we graphed it, it looked like it was a root, we divided through synthetically by it, we confirmed it was a root, because we have a remainder 0, and then you have to look at your quotient, okay, and see if there's any additional roots you can get from that. Just like we did here. Okay, we divided through synthetically, we got a root that was -1, but then we still have to look at our quotient. In this case, it did factor nicely. We didn't need the quadratic formula. And we got -1 as a root, which was repeated, and 2 as a root. Okay? So this one did give us additional answers when we looked at the quotient. This one does not. Okay, so it's just x equals 1/2. Let's look at this one. Same as the last two. Okay, so it says to find all real zeros and classify them as rational or irrational. At most, there could be 3, because it's a cubic. So you're not going to have more than 3 answers. So let's see what we got. So factors of my constant. Not that many. Factors of my leading coefficient. So for rational roots, I could have positive or -1, positive or -2, positive or -1/3, and positive or -2/3. 1/3 and 2/3, that's pretty close. We might have to zoom in if it looks like there's a root there. Okay, so now that I've got my list of possibilities, I want to narrow that down. Yep, I'll go back 1 second. So you get 3x cubed minus 8x squared plus x plus 2. Okay, I'm looking at it. It looks like, well, it looks like there's a couple possibilities. Let's zoom in. Looks like 2/3 could be a root. Okay, let me trace over and just kind of get an idea. I'm pretty sure 2/3 is a root. So let's, maybe -1/3 is as well. Okay, but let's divide through by 2/3. And we're going to have 3, -8, 1, 2. 2/3 times 3, that's going to give me 2. -8 plus 2 is -6. Okay, -6 times 2/3, the way you could do it if you get stuck is do -6 times 2, that's -12, and then divide by 3, -4. -4 plus 1 is -3. -3 times 2 is -6, and -6 divided by 3, -2. And I get a remainder of 0. Okay, so I proved 2/3 is a root. Okay, that's one answer. Okay, next, I'm going to look at my quotient. Okay, and I have to see, are there any additional roots I can get from that? 3x squared minus 6x minus 3. First thing I'd do is just take a 3 out of everything. So you get x squared minus 2x minus 1. And will that factor? X squared minus 2x minus 1. Anybody think that'll factor? It won't factor, because your signs have to be one of each. So if you try to factor it, the only way you can get 1 is to do 1 times 1. But that's not going to give you a -2 in the middle. All right, so factoring this won't work. Darren, what's the other way we could solve that quadratic equation? Yeah, we can check the discriminant, and if the discriminant works, which in this case you're going to get Yeah, in this case, the discriminant's good to go. We're going to be positive. So how would we actually solve it?
So negative 2 squared minus 4 times 1 times negative 1
Yeah, what's the name of what you're doing?
discriminant.
No, discriminant's only part of the thing you're using. Brielle, what's the name of that? Quadratic formula. Okay, if you can't factor a quadratic, you have to use the quadratic formula. Or you can complete the square. Most people don't like that. So we'll use the quadratic formula. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So minus a minus becomes a plus. That's why I said the discriminant is good. It's going to work. Unfortunately, when the discriminant's positive, all it tells you is, yep, it works. Still have to go through and do it to find the answers. So 2 plus or minus the square root of 4 times 1 times 1 is 4. So we get that, which will simplify to square root of 8. You can write as 2 root 2. And the reason I did that is because now I can cancel a 2 out. 1, 1, 1. So the answer is 1 plus or minus root 2. Those are all the answers to that problem. 2/3 is rational. The other two answers, 1 plus or minus root 2, irrational. Anytime you take a square root of a number that's not a perfect square, it's irrational. Okay, so the really important thing here is you have to be able to find at least one root to start. If you can't, you're never going to be able to get this cubic equation down to a quadratic. Okay, so I'll always give you a problem that has at least one rational root, and then you divide through synthetically by it. And the last idea is what's called the upper and lower bound. Okay, so an upper bound, okay, a number is an upper bound for a function if f of x is never equal to 0 when you pick a number bigger than that upper bound. So what that's saying is it guarantees me that, let's say 7 was an upper bound. What you're telling me is that if you look past 7, you will never find a root. You're telling me 7 is a limit on how high you have to look for roots. It's an upper bound. Okay, and same idea with a lower bound. Okay, it says a number d, okay, is a lower bound for the set of real zeros if f of x is never equal to 0 when you look below that number. So let's say you tell me -5 is a lower bound. You're saying that if I look lower than -5, I will never find a root. -5 is the lowest possible number you would ever have to look at to find a root. Okay, the way our book does it, upper bounds will always be positive, lower bounds will always be negative. That's just the way the theorem is going to work. So it doesn't tell you what the root is, but it gives you an interval. It kind of narrows down where you have to look. That's the idea of an upper and lower bound. So the theorem with this is the upper bound theorem. And to use this theorem, all you have to know how to do is do synthetic division. Okay? And there's two ways you can read this theorem. So I've written it both ways, and I'll show you how you can read it. So let's suppose you have a polynomial, and the first coefficient is a positive. Okay? A polynomial with a positive leading coefficient. And let C be a positive number that you think is an upper bound. To check if it's an upper bound, you're going to do synthetic division with that number, C. And if you do the synthetic division and the very last line contains no negative numbers, then C is an upper bound. So you're not so much looking at the numbers, you're looking at the sign of the numbers. Okay. And you could also look at it one other way. Suppose that f is a polynomial and the leading coefficient is negative. Right? And you think you have a number that's an upper bound. To check if it's an upper bound, do the synthetic division and make sure that the last line doesn't contain any positives. If your last line does not contain any positives, then the number that you said is an upper bound. So you just have to remember, if it's a positive leading coefficient, you're looking for the last line to not contain negatives. 0 is okay, but no negatives. If your leading coefficient is a negative, when you do synthetic division, you're making sure the last line doesn't contain any positive values in order to confirm that your number is an upper bound. Okay, so here's a problem you could have. Show 3 is an upper bound for that polynomial. Meaning that if you start to look after the number 3, you'll never find a root. I'm telling you, 3 is as high as you need to look. So, we're going to do the synthetic division and see what we get. Okay, so start with 3 on the outside. Put down your coefficients. Just do the synthetic division. What am I hoping for here? That I don't get any what? In the last row. James?
Negative numbers.
No negatives. Okay. My leading coefficient was positive, so I'm hoping that I don't get any negatives. No negatives. If I don't get any negatives, then 3 is an upper bound. Okay, so let's check. First number I get is 1. That's positive, so that's good. 3 times 1 is 3. Negative 3 plus 3 is 0. Is 0 negative? Nope, so I'm still okay. It's not positive, but I said I don't want any negatives, so 0 is fine. 3 times 0 is 0. 1 plus 0 is 1. That's positive. 3 times 1 is 3. 3 plus negative 1 is 2. So the last row does not contain any negatives, which means 3 is an upper bound. Okay? So if you graph this, you'll never find a root higher than x equals 3. I guarantee it. And to do a lower bound, we don't really have another theorem. We just do an upper bound. Okay? So if you have a lower bound problem, you're going to change it to an upper bound problem. So we can just do the same thing again. Okay. The idea is that a number is a lower bound if the opposite of the number is an upper bound in that function. Okay, so a number is a lower bound if the opposite of the number is an upper bound in that function. So in this one, I'm not going to go through the whole thing, but let me just show you the polynomial you would use. To do a lower bound problem, you can't use f of x. You have to use f of negative x, which would be just changing all your x's to negatives. Now, sometimes the negative will cancel out, especially on a square. On an odd, though, it won't. So it would become negative x cubed plus 2x squared. That's a negative 21 times a negative x becomes plus 21x and plus 16. So sometimes some of the signs change a little bit from f of x. So now you would use this and confirm that 6 is an upper bound. And that would prove that negative 6 is a lower bound. You'd just do the synthetic division with 6. And then do it out. Yeah, we can go through a lower bound if we need to tomorrow. Okay, so synthetic division is very important for tonight's homework. You'll use it quite a bit. Okay, so the homework is on 183. Okay, and the numbers are 1, 2, 5, 6, 9, 10, 13, 14, 17, 18, 27, 31, and 32. So it jumps around quite a bit. We'll take a look at that tomorrow, and we'll finish up our material for the week tomorrow and then test on Thursday.